Hi everyone, I welcome you to this YouTube channel where we shall be actually learning physics with IBM. My name is IBM and I welcome you to yet another episode of Learning Physics with me. In this lesson, we shall actually be learning some of the concepts of AS, but don't forget to subscribe, like, comment, and share the information that you'll find on this YouTube channel. It will be very instrumental in passing your AS physics, and of course, those studying IGCSE, your time will also come. I will upload videos for IGCSE. For now, I would like to welcome those who are studying AS, and I will be introducing errors and uncertainties. To begin with, I want to help you to draw the difference between the most important concepts in errors or uncertainties. And these are actually the two terms. This is the two terms that are very important in errors and accuracy. I mean, errors and uncertainties. These are basically accuracy and precision. This is lesson 1 of errors and uncertainties. Of course, you can always watch out for lesson 2. There will also be lesson 3 for errors and uncertainties. And basically, lesson 3 will be about worked examples or solved examples in past paper questions, which will help you to be confident with errors and uncertainties. Okay, so to begin with, let's concentrate on accuracy. We normally use the word accuracy in our everyday spoken language, but what is accuracy as far as measurements are concerned? A measurement is bound to be accurate and it is bound to be precise. What do we mean by those two terms? Today I want us to draw a difference between accuracy and precision. This is all under errors and uncertainties. To begin with, a measurement could be taken or measurements could be taken, but when an expected value or an accepted value or a true value is actually known, then the degree to which those measurements taken are close to the accepted value is what we call accuracy. So it means measurements are very accurate if they are very close to the expected value or they are very close to the accurate value. The degree to which measurements are close to the expected value, to the true value, to the accepted value is what we are going to call accuracy. That means accuracy, if values or measured values are very accurate, then there will be a small difference between the true value and the expected value. In fact, the average value of repeated measurements is actually going to be the true value. Think of a situation when you take several values of measuring acceleration due to gravity, and you know that the accepted value of acceleration due to gravity is 9.81, that is meters per second squared. So if you take several values of g and their average is very close to 9.81, it means the average value of g is giving a value very close to 9.81, then we can say the measurements are actually very accurate. So measurements which are very close to the true value can be considered to be accurate, and therefore accuracy is the degree to which a measured value approaches, the degree to which a measured value is close to the true value. That is what we call accuracy. So measurements will only be deemed to be accurate if they have a small, or if their average has a smaller difference from the true value. So what affects accuracy? Accuracy is going to depend on one. It will depend on the equipment that is being used for a measurement. And also it will depend on the skill that is being used by the experimenter. For instance, you may use an equipment which before taking any measurement, it is giving a value. Therefore, what does that mean? It means that the values will always deviate from the expected value by a certain amount. Therefore, You need to improve the skill of taking the measurement or the technique of taking the measurement. How? If only you can identify that reading of that instrument before a measurement is being taken, then you can eliminate the error, which we shall later on call a systematic uncertainty or systematic error. And therefore, by removing a systematic error, the measured values will always be very close, or their average will be very close to the accepted value. So this is now going to be an experimental technique. First of all, you identify the error in the instrument. And secondly, every time you take a measurement, maybe you subtract or you add the uncertainty or the error in that instrument so that the measured values do not deviate from the true value. In conclusion, I'm saying accuracy refers to how close the measured values are to the true value. How close the average of measured values is to the true value. That is what we are going to call accuracy. On the other hand, what do we mean by precision? What do we mean by precision? On the other hand, what do we mean by precision? So precision, in everyday life, we talk about being precise. Being precise, what do we mean? Anyway, the English meaning of being precise may not be the same as precision in taking measurements. Sometimes you may take measurements which are actually which are repeated, but when these measurements are not exactly the same values every time you repeat a measurement. For instance, in measuring the diameter of a wire, which is very small using a micrometer screw gauge, many times you take measurements around the wire at different points of the wire. And from experiments, you must have noticed that actually the best value of the measurements is actually the average of those values. So what therefore do we mean by precision? Let us assume you have taken repeated measurements several times. And if the measured values are almost the same, then we say they are actually precise. If they are almost the same, it means the range of such values is therefore very small. The range is very small. So the range of such values is very small. So it means if values are said to be precise, the range between them is very small. And if the range between them is very small, it means these values are very close to each other. Therefore, we can say that precision refers to how close measured values are to each other. Even though they may not be accurate, even though they may not be close to the true value, even though their average may not be close to the true value or to the accepted value, but how close are they to each other? That's what we call precision. So the degree to which a measured value can be reproduced several times is what we call a precision. If a measured value is reproduced, it means every time I repeat the experiment or every time I repeat the measurement, I get almost the same measurement. Therefore, the measurement, the range between the first attempt and the second attempt is approximately zero or very small. Therefore, we can say measurements are extremely precise. So let's think about a simple scenario here. An ASC student takes measurements, find the acceleration due to gravity g, which we know as being 9.81. Unfortunately, he observes that the first attempt of G1 gives him values such as 4.92. When he repeats the experiment for G2, he gets 4.91. He repeats the experiment, he gets for the third time and gets 4.90. He repeats the experiment for the fourth time and maybe gets 4.92. You notice that these values are very close to each other. All these values, the student was trying to measure the acceleration due to gravity. We can say because they are very close to each other, they are just differing in a very small value, they have a very small range. So we conclude by saying that these values are precise. However, Since we know the true value or the accepted value of acceleration due to gravity as 9.81, the average of these two values is far from 9.81. That means they are actually precise, but they are not accurate. So this is now the difference between precision and accuracy. Measured values could be precise if they are very close to each other. Therefore, they have a small range. However, they may not be accurate, as we have seen. So what does this imply? We now notice that a precision makes values to scatter around a certain value, which could be sometimes the true value or sometimes not. So if precision affects value or makes values to scatter or to spread, then the best value of such values is just the average. So the precision of an instrument is sometimes determined by maybe the smallest division on the scale, on the measurement scale of that instrument. But before we go to that, I want people to be able to draw the difference between accuracy and precision. A measured value can be precise, or measured values can be precise but not accurate, as we have seen. But is it possible for accurate values not to be precise? We are going to see that later on. So, precision is making values to scatter or to spread, and sometimes they may not necessarily spread around the true value. Sometimes they may not spread around the true value, but they will be close to each other. So we can see that the precision is bad if the range is very wide. That is precision. So the degree to which measured values are close to each other is what we are calling precision. The degree to which measured values are to each other is what we are going to call precision. I think I've given a simple demonstration of acceleration due to gravity, where a student tried to measure acceleration due to gravity, and for 4 different attempts, the student came up with those 4 different values. And yet the expected value of acceleration due to gravity is 9.81. So the values obtained by the student were very precise because they were very close to each other. The range was very small. Unfortunately, their average would not even give us the true value. Therefore, we say, yes, they were precise, but they were not actually accurate. So, what therefore determines precision? Earlier on, we said that for accuracy, we could identify an error in the instrument being used, and then we change or improve our experimenting technique. If I identify that the instrument has an error before being used, then every time I use the instrument, I make sure I eliminate the error. That means I will be improving accuracy. But then precision makes values to scatter around a true value. That means it is not depending, many times it will not depend on the experimenter. It is actually, there could be something that can be unavoided, that cannot be avoided, and that could cause the precision to always be affected. So, as accuracy was affected, or accuracy was actually determined by the systematic error, precision is going to be determined by another type of error, which we shall later on discuss in details, and this is the random error. I want you to note very well that a precision is that part of accuracy which is within the control of the experiment. It is that part of accuracy which is within the control of the experiment. The experimenter may choose different measuring instruments and may also use them with different levels of skill, and this will affect the precision of the measurement. It is that part of accuracy which is within the control of the experiment. Now, suppose let's assume we want to measure the diameter. Let us assume we want to measure the diameter of Let's assume we want to measure the diameter of a steel sphere. There are several instruments we could use in the laboratory. Number one, you could use a ruler to measure the diameter. You could use a vernier caliper, or precisely a digital vernier caliper. You could also use a micrometer screw gauge to measure the diameter. But then, will all the instruments give the same values? I gave a simple analogy here that if a measurement of the diameter of a sphere is taken using a ruler measures to 1 decimal place, so we expect a value to be approximately 1.3 plus or minus 0.1 centimeters, where this is going to be the expected uncertainty in taking a measurement using the ruler. If the same measurement is taken this time using a vernier caliper, of course another decimal place is introduced because the vernier caliper measures to 2 decimal places in centimeters. Then if a micrometer screw gauge is used, again another decimal place is most likely going to be introduced because the micrometer screw gauge measures to 3 decimal places in centimeters. Therefore, if I am using, for example, the ruler to take measurements, even if I take several measurements using the ruler, these measurements, if the first measurement is say 1.3 as listed here, and the second measurement is 1.4, that means the difference in the two values, which is going to be the range, is going to be 0.1 centimeters. But if I use a vernier caliper, there is a likelihood that the values will only differ in the last digit. For instance, the first measurement is 1.31, and when I repeat the measurement, maybe it is 1.32. You notice that in this case, the range is 0.01 in centimeters. So this range is far smaller than this range here. If I use a micrometer screw gauge and the measurement is approximately this, maybe if for the first attempt I have 1.312, for the second attempt I could be having 1.31, I expect that the values are most likely going to differ in the last digit. Maybe this is 3. The range or the difference between these two values is actually 0.001 centimeters. So you notice that this range is far smaller than this range here. It is also smaller than this range. What does that mean? So these two values, 1.312 and 1.313, are very close to each other. Therefore, we can say that these two values are very precise. They are more precise compared to these other values here. So we would say in measuring the diameter of a steel sphere, the micrometer screw gauge is more precise than the meter ruler. In measuring the diameter of a steel sphere, the micrometer screw gauge is more precise than the meter ruler. So it's like precision is somehow related to the number of the small places to which an instrument takes or gives a measurement. In the laboratory, for example, there are stopwatches which measure to 1 decimal place. You have also seen stopwatches which measure to 2 decimal places. So it means a stopwatch which will be measuring to 2 decimal places would give more precise values than one which would measure to 1 decimal place. By the way, I want you to note that the number of significant figures quoted for a measurement is increasing as the precision of the instrument also increases. In fact, the number of significant figures is actually, or in a measurement, gives an indication of the precision of the measurement and the instrument that has been used. When I see a measurement or a length given as 1.3 centimeters, in my mind I know this is most likely a ruler that has been used to take such a measurement. When I see a length which has been quoted as 1.312 in centimeters, In my mind, I am very certain that the instrument used here is most likely an instrument which measures to 3 decimal places in centimeters. This is most likely a micrometer screw gauge. So what am I trying to derive at? The more the number of significant figures, the higher the precision. The more the number of significant figures that an instrument gives a measurement, the more precise that instrument is. But to fully understand precision and accuracy, let's first draw an analogy between precision and accuracy. So we are going to first of all I want us to observe. We have already observed the number of significant figures in the previous demonstration, in the previous illustration, and we have seen that actually the meter ruler is less precise than the micrometer screw gauge. And we have said the number of significant figures to which a measurement gives a reading is analogous to the precision of that instrument which has been used. So that analogy has already been seen, but let's draw a better analogy using many of you play darts or have played darts. I want us to use a simpler analogy here. Number one, we have 3 demonstrations here. We are going to call the inner circle here the target, our target. Uh, attempt 1, attempt 2, and attempt 3. Let's say 3 people are playing darts. And the first person drops 2, or let's use a simple shooting bullets maybe. So in the target, for the first person, we have two bullets in the target. For the second person, there is no bullet in the target. For the third person, all bullets are in the target. So one, because the first person has some bullets in the target, there are 1, 2, 3, 4, 5, 6, 7, 8 bullets, and at least 2 are in the target. So we can say there is some kind of accuracy in such an attempt. So the accuracy is quite moderate. I use the word moderate. We can't say there was no accuracy when 2 bullets were in the target. For the second attempt, there is completely no bullet in the target. Therefore, we can say there is extremely poor accuracy or no accuracy at all. But then you will notice that these bullets are hitting almost the same point. Although they are not in the target, they are close to each other. Then this takes us back to precision. We say the values can be close to each other even when they are not accurate. The bullets have hit spots close to each other even when they have not hit in the target. So in part 2, we say precision is good, but accuracy is actually poor. In part 3, we see that we have all the bullets in the target. And because all the bullets in the target are in the target, then we say accuracy is good. But then, when all the bullets are in the target, they are also close to each other. Therefore, we say that even precision is good. Now, this takes us to our mathematical concepts. Which one could imply the other? Can we say that when precision is good, accuracy must automatically be good? Or we can say that when accuracy is good, then the precision is good. Which one would imply the other? So, we have seen that the first diagram is showing moderate accuracy but poor precision. The second diagram is showing good precision but poor accuracy, no accuracy at all. The third diagram is showing that there is good precision and good accuracy. What conclusion can we make from that? So precision has or is partly to do with accuracy of an observation or measurement. By the way, a reading may be very precise but does not need to be accurate. But fortunately, Accuracy is concerned with how close a reading is to the true value. We have already seen that a micrometer screw gauge is more precise than a meter ruler. But if a micrometer screw gauge has an error, then the readings will be either above or below the true value or the expected value. Therefore, accuracy would be very poor. So we are saying precision is partly to do with the accuracy of an observation. And we have said a reading does not need to be accurate in order to be precise. But in most cases, when measurements are accurate, they tend to be precise. That's why you see in the third demonstration, when all measurements hit the target, they are very close to each other. When all the bullets hit the target, they are very close to each other. Therefore, they are relatively precise. So, precision does not imply accuracy, but sometimes accuracy can imply precision. Let's see further illustrations to fully understand the difference between accuracy and precision. Further illustrations. So we have seen these are measurement. The dots are showing measurements which have been taken, and they are actually scattering around. When a line of best fit is drawn, you see that most of these measurements are close to the line of best fit. Because the measurements are close to the line of best fit, then we can conclude that the measurements are actually precise, and they are also good. There is good accuracy, there is good precision. In the second case, you see that a few measurements can only be very close to the line of best fit. So still, we can say there is some accuracy. Accuracy is good, but you notice that the range between the values is relatively wider. Second, on the third attempt, in the third demonstration, you see that all values are below the line of best fit, or the true value. Actually, this line is showing the true value, the accepted value of x. This is most likely because there is poor accuracy. Later on, we shall see that it could be because there is a systematic error. In the last attempt, we see that the values are also almost above the true value or the accepted value, and they are also having a relatively wider range between them. So we can still conclude by saying that here, even though the accuracy is bad, even the precision is actually bad. Therefore, we can also understand accuracy by such. Remember, accuracy and precision are always going to be used in measurements, and you should be able to actually distinguish the two terms very well. Learn the difference between accuracy and precision. Know the difference between accuracy and precision. We can also demonstrate accuracy and precision using distribution graphs, as we can see, or probability density graphs. So let us assume that the vertical line here is representing the expected value of a measurement. But yet the values you obtain during measurements when the graph is plotted, or when the distribution curve is plotted, they form an average value which is around this peak here. So you notice that there is a big deviation of the average value of all these measurements from the true value. So it means the further the average of this value is from the true value, the poorer the accuracy. But the narrower this is, the higher the precision. So it means precision is not affected by accuracy. Precision values can be precise even when they are not accurate. Values can be precise even when they are not accurate. So let's see a better distinction. Let's look at this. This is a probability density against the edge. So measurements have been taken, and when the distribution curve is drawn, the average is here. So you see this is showing a range between the true value. This is the true value of the h, and this is the average value of the values that has been taken, or the measurements that have been taken. You see that in comparison of the peaks of the size of these distribution curves, you see that this is small, this is small, this is large, and maybe this is relatively large. So when the peaks are narrower, then we say the precision is high. When the peaks are narrower, we say the precision is high, because when the peaks are narrow, it means the range between the values is smaller. So here we have high accuracy, here we have high accuracy. I mean precision high, high precision. High precision because of the narrow peaks. Yet here we see that the precision will be low, and the precision will be low because of the relatively wider peaks. All the distribution graphs are relatively wider. But then let's see the deviation from the true value, because accuracy is determined by how close the measured values are to the true value. How close is the average of all these measurements to the true value? So when you look at the last graph, you notice that the average of the measured values is actually the true value. So here the values are actually precise, and they are also accurate. Here there is a range between the true value and the average of these values. So we shall say here the accuracy is extremely poor. Here we can see that the difference between the true value and the average of the values is very small. So we can also say that the accuracy is relatively high in this case. Here we see that the range between the true value and the average of the values is very wide. Therefore, there is low accuracy and there is low precision. In conclusion, I'm saying precision refers to how close the measured values are to each other. That affects, or that makes the values to be either close to each other, that is for high precision, and far from each other for low precision. Yet accuracy refers to how close the measured values are to the true value, or the accepted value, or the expected value. So the further the values are to, or the further the average is to the expected value, the lower the accuracy. The closer the average is to the expected value, the higher the accuracy. Let's use another demonstration, maybe, but this one you'll try it at your free time, or you can pause the video and try to attempt this. In this exercise, you have been given 3 spots, or 3 attempts. The figure shows results of rifle shots to a target using the words like precise, imprecise, accurate, and inaccurate. Describe the observation above. For simplicity, I will attempt this for you. Number 1. In A, you notice that there are some shots in the target. So we shall say this is actually accurate. This will be accurate because there are some shots in the target. So it is accurate. But also you notice that there, at least most of them are close to each other. So you can say accurate and actually precise. In B, this is supposed to be B and this is supposed to be C. In B, you notice that there is nothing in the target, so we can say this is actually inaccurate. Inaccurate. But you notice that all these shots are concentrating in this position here. Therefore, we can say, although they are inaccurate, then it is actually precise. In C, we notice that actually the shots are scattered all over. Although there is some shot in the target, but actually they are scattered all over. Of course, we can say precision is bad, so it is imprecise. Precision is bad, so it is imprecise. However, we can't say that accuracy is bad, because since all these values are scattered, all these shots are scattered around, there is also something in the target. So it is also accurate, although the accuracy is relatively not very good. It is relatively accurate. So you notice, precision would refer to how close the measured values are to each other without minding about whether they are accurate or not. Accuracy would concentrate on how close the measured values will be to actually the true value. Example number 2 is going to be yours. So you have a table. The measurements have been represented by vertical bars or vertical lines. So you have the first row, the second row, and the third row plus the fourth row. Please pause this video and actually complete this table. Pause the video and complete the table. Okay, let us proceed. In summary, when we talk about precision, basically we are referring to spreading about average values, scattering about average values. And when we talk about accuracy, we are talking about how close measured values are to the true value or nearness to the actual value. We have seen that precision will affect a random error, is affected by a random error. We are going to see what a random error is. And accuracy, because it basically depends on the instrument, it is affected by a systematic error. How do we improve accuracy? We can always repeat and take the average, or we can repeat and plot a graph. Sometimes the average reduces the average value is better than a single value, because sometimes, because values scatter around a certain value or a certain average, sometimes the average is the best. Plotting a graph, we draw the line of best fit. The line of best fit also would be better than considering a single value. On the other hand, accuracy can only be improved by a good technique. Identify a systematic error, and whenever you're using the instrument, remove the systematic error or add the systematic error. And then this would also improve accuracy. When we look at a graph, which feature do we see to identify that there is an issue with the precision? So scattering about a straight line, we know that there is precision is not good. When the scattering is very wide, it means the range between the values is the range between values or the range between the highest and lowest value is very wide. Then for accuracy, if we draw a line, a straight line through our points, and that line is parallel to the line of best fit, then we know that there is a problem with accuracy. So that is a summary of accuracy and precision. Next, then we should talk about uncertainty. And I think apart from accuracy and precision, one of the most important concepts here is uncertainty. What do we mean by uncertainty? I think in everyday life, the word uncertainty refers to things maybe we don't expect, things we don't, or things which come to us without our can I say preparation, without preparing for them, things we really don't hope for to expect, but for to happen, but then they end up happening. Now, in measurements or in physics, no measurements are actually absolute. By the way, absolutism is the opposite of relativity. Remember, in relativity, we say measurement, quantities or things in life have significance in comparison to others. That's what we mean by relativity. In measurements, there are no measurements which are actually absolute. In fact, in real life, precision is not the only factor which affects accuracy of a measurement. In fact, The range of values within a measurement is expected to lie or to fall, is what we shall call uncertainty in measurement. Unlike the uncertainties you talk about in everyday life, things you do not expect to happen and they all of a sudden happen. In measurements, uncertainty would be referring to a range of values within which a measurement is expected to fall. For example, I gave an example here. You have taken a measurement and it is 26.0 plus or minus 0.5 centimeters. Actually, because it is to one decimal place, I know that this is a meter ruler. This measurement implies that this value here can be as high as 26.0 plus 0.5, which gives you 26.5, or it can be as low as 26.0 minus 0.5, which can be 25.5 centimeters. But the most likely expected value is the value which I have quoted here, that is 26.0 centimeters. Therefore, this other part, plus or minus 0.5, gives an allowance for the values which are obtained in a measurement to take values between the highest, which is 26.5, and the lowest, 25.5. So a measurement will take any value between that range. So the uncertainty plus or minus 0.5 gives allowance for the measured values to fall within that range. By the way, whenever we are writing measurements, the number of significant figures on a measurement gives some information about the uncertainty. In fact, the number of significant figures gives some information about the uncertainty of the instrument. The number of significant figures of the measurement will indicate its uncertainty. Before we go to the details of that, some instruments have what we call the limits of reading uncertainties. Let's see what are some of these limits of reading uncertainties. Some instruments which are actually analog instruments, such as you have seen, look at a protractor where you have to look at a scale, and the scale divisions of a protractor are very close to each other. For such a protractor, the limit of reading that in that protractor is equal to actually the smallest division. For a protractor, the smallest division is 1 degree for a protractor. That means the limit of taking a reading from a protractor is 1 degree. The other word that we could use for such a limit would be the least count. So we say that the least count of a protractor is 1 degree. Later on, we shall say for such instruments where the divisions are extremely fine and close to each other, the smallest value that the instrument can give can be considered to be its uncertainty. So there is no problem for me to say that the uncertainty in taking a reading from a protractor is plus or minus 1 degree. Sometimes, when the divisions are fairly large, like for a meter ruler, the uncertainty is sometimes taken to be half of the smallest division. Even some other analog meters have fairly large divisions. Therefore, the uncertainty can be taken as half of the smallest division. For example, the limit of reading is 0.1 centimeters for the meter ruler, for example, but this is because on each side of the meter ruler, the uncertainty could be half of 0.1, so that the total, as we shall see later on, is actually 0.1 in centimeters. So if the limit of a reading is 0.1 centimeters, then the uncertainty range could be half of this value here. which when you divide, you get 0.05 in centimeters. This is sometimes going to be called the absolute uncertainty because it will always have the same unit as the measured value itself. How about digital instruments? For digital instruments, such as this one, here I have a simple demonstration of a millivoltmeter. It is reading 29.7. This last digit is to one decimal place, and this last digit will give me it will give me a picture of the smallest value which this instrument can read. And remember, the smallest value, we call it the least count. So the last digit is to one decimal place. By common sense, the smallest value this instrument can give is most likely 0.0. It is, let me get a rubber. The smallest value it can read is 0.1. Because it is reading 29.7, that is to one decimal place. The smallest digit to one decimal place is 0.1. We call this the least count. So the smallest value this instrument can measure is 0.1, which is the least count. So this will be its absolute uncertainty, or the uncertainty in using this instrument. So think of a stopwatch that you normally use in the laboratory. And let's say it displays 25. Of course, it displays 0, 20, then it puts here you have 42. That means this time would be interpreted as 20.42 in seconds. These are two decimal places. The smallest digit this stopwatch could read would be 0.01 to two decimal places. So 0.01 is going to be the least value which this stopwatch can give, and it is its least count. Therefore, the uncertainty in such a stopwatch would be plus or minus 0.01 in seconds. Remember, this is in minutes, this is in seconds, this is in 100th of a second. That's why I have here 20.42. So for digital scales, the uncertainty is taken as the smallest scale reading, which we shall precisely call the least count. So if I know the least count, I can fully and easily tell the uncertainty in that instrument. Okay, so we have here some examples. I gave you a stopwatch which has divisions of 0.1 seconds, or a stopwatch which measures to 0.1 seconds. Its uncertainty is 0.1. And a typical value that could be given, you notice that the values are to one decimal place. Then there are those stopwatches, the most common ones used in the laboratory, measure at two decimal places. If it gives such a value, the least count is 0.201. When it comes to temperature, the readings of the thermometer are relatively, most thermometers measure to 0.5 degrees Celsius. Therefore, the uncertainty is approximately 0.5 degrees Celsius. That is half a division. And of course, for one division being 1 degree Celsius, therefore we estimate the uncertainty as half of a division. And most meters, especially analog meters, measure to 0.1 ampere as the least count. Therefore, the uncertainty can be 0.1. Now, I want you to note that in reading, the uncertainty in a reading is not wholly or fully confined to the reading of its scale, or even to the skill of the experimenter. Any measuring instrument sometimes has a built-in uncertainty. Take, for instance, a meter ruler expands as its temperature is increased, or as temperatures rise. The readings of the scale will therefore be precise at only one temperature, and they will be imprecise at other temperatures. Therefore, there will be an uncertainty due to expansion of the scale. That is for a metallic meter ruler. Suppose I know by how much the ruler is most likely going to expand, then I will be able to improve the precision. I would be able to remove the uncertainty and improve the precision if I can determine by how much the ruler is most likely going to expand when temperatures change. For some other instruments, especially digital instruments like digital meters, manufacturers normally quote the uncertainties for each meter. I will give an example. I think I gave an example here. For some instruments, manufacturers quote the most likely uncertainty for that particular instrument. For example, you will find a digital voltmeter which has been quoted as plus or minus 1%, plus or minus 2 digits. And this means the 1% will apply to the total reading, which is seen on the scale. And then the plus or minus 2 digits is going to be the uncertainty in the final display on the figure. The uncertainty in the final display of the figure. I gave an example. We have a meter reading 2.00 volts. It means for the first uncertainty plus or minus 1%, the uncertainty, we change this from percentage to be 1 over 100 times 2. But then there is another uncertainty which is plus or minus 2 digits, and we said this is the uncertainty in the final display of the figure. So instead of having the uncertainty as 1 over 100 times 2.0, we shall have plus or minus 0.02, because here we have 2 digits. Of course, the first digit would be 0.01, then the second digit will be 0.02. So since we have plus or minus 2 digits, and this is the uncertainty in the final display will be to 2 decimal places. Therefore, our total uncertainty will be plus or minus 0.04. So we add up those uncertainties. Sometimes there are fluctuations, or there could be fluctuations in measurements. And if there are fluctuations in measurements, then what happens? Actually, the uncertainties simply accumulate. For any fluctuations, the uncertainty in a measurement, which is sometimes referred to as an error, these uncertainties simply accumulate. The uncertainty would simply be added to any further uncertainty which is caused due to any fluctuations. Therefore, the uncertainty in a measurement is not or is sometimes going to be called an error, but this does not mean a mistake. Of course, in our everyday spoken language, error would imply that there is a mistake or a mistake has been made. But here there is no mistake in taking a measurement, but there is always some doubt or some uncertainty in its value. So here we are going to use the word uncertainty to mean or to refer to some doubt in a measured value. And that doubt, although we shall use the word error, it may not always, or it will not always refer to a mistake. Okay, if you have understood that concept, perhaps you will be able to attempt this self-check. A student takes a large number of imprecise readings for the current in a wire. He uses an ammeter with a zero error. Remember, okay, a zero error, we shall say zero error, which is given as negative delta I, meaning that all scale readings are too small by delta I. That means when I get their average will be smaller than the expected value. Sketch a distribution curve of the number of readings plotted against the value of the current. Maybe I can attempt this for you. So I am sketching a distribution curve here. So let's say this is the true value of I. And they have said that all measured values uses an ammeter with a zero error of minus delta I, meaning all scale readings are too small by delta I. So let the average of those values be to the left because it is minus. So it means the average of this, are they precise? They are imprecise. So it means the distribution curve is going to be relatively wider. I want to draw a relatively wider distribution graph here. So relatively wider distribution graph, and its average, the peak, is this side, giving us delta I this side. So there is a range between the two what? The true value and the average of all these values. So this is where I have delta I. So you notice the true value is above because they said all scale readings are too small by delta I. So all values, their average is going to be actually to the left of the true value because they are all too small. They are smaller than the expected value. So that will be my distribution curve. This is of course going to be current, measured values of I, current. Okay, then you can attempt number 2. You should be able to attempt number 2. You can draw a similar distribution graph to show those values. Okay, sorry. I'll try number 3 for you. The manufacturer of a digital ammeter quotes its uncertainty. It is quoted as plus or minus 1%, plus or minus 2 digits. Determine the uncertainty in a constant reading. So in this reading here, in that reading there, the uncertainty are using plus or minus 1.5. The uncertainty in that will be actually 1.5 divided by 100 times 2.64. And when you press your calculator, let me check my calculator here. 1.5 divided by 100 times 2.64. So this would be actually the uncertainty due to 1.5% would be actually 0.0396. But then there is an uncertainty in the final display which is actually plus or minus 2 digits. So that means that I will add here plus 0.0, it is 2 digits, so that will be 0.02. Note that when I round off this to one significant figure, it will be 0.04. So the total uncertainty will therefore be 0.06 amperes, plus or minus. So that will be the uncertainty in this reading here. Therefore, I could write this as 2.64 plus or minus 0.06 as my value of current with its corresponding uncertainty. Then in the second part, the meter is used to measure the current from a DC power supply. The current is found to fluctuate randomly between this value and that value. Determine the most likely value of the current. Of course, the most likely value is the average value. So the most likely value of current will be equal to 1.98 plus 2.04 divided by 2. I'm finding the average. 1.98 plus 2.04 divided by 2. This will be equal to 2.01. But then, because of the fluctuations, there will be also another uncertainty in this value. The uncertainty in this value will actually be times 1 point. Okay, let me just get the uncertainty. So the uncertainty in this value, the uncertainty in the average value for the fluctuations will actually be 1.5 divided by 100 times 2.01. So that one, 2.01 times 1.5 divided by 100, this gives me 0.03. But remember, the uncertainty due to fluctuations must be added to the uncertainty in the stable or constant reading. Therefore, the most appropriate uncertainty here, the most appropriate uncertainty in the final value is actually going to be 0.03 plus the uncertainty in the constant reading, which is 0.06. Therefore, the value, the most likely value of the current is going to be 2.01 plus or minus 0.09. So that will be the value of the current and its uncertainty. Note that I had already found the uncertainty in the stable value, which was 0.06. Initially, we consider this as being a constant reading, but then the current is found to fluctuate randomly. Because of the fluctuations, the uncertainty in the average value must be added to the uncertainty in the constant value. That's why the most likely value of current is going to be that average plus a higher uncertainty due to fluctuations. Okay. Next, further examples will be in the solved past paper questions, so that one is not a problem. Next, we can talk about the choice of instruments. So the precision of an instrument required for a particular measurement is somehow related to the measurement being made. Think of a situation where you are to measure the diameter of a single strand of your hair on your head. I don't think that even a micrometer screw gauge would be very good to give the diameter of the hair on your head. But maybe it would be better than a vernier caliper. It would be better than a meter rule. So in the same way, it would be not advisable for you to use a galvanometer to measure very tiny currents. In other words, okay, you would use a galvanometer to measure currents of a few milliamperes, but there would be a better instrument that you would use if the currents involved are very small. You could even use a microammeter to measure very, very small currents. Therefore, we are saying choice is often fairly obvious where single measurements are taken, but care has to be taken where two readings are subtracted. For example, we have the distance of a lens from a fixed point, and it has been measured using a meter ruler. Remember, a meter ruler measures to one decimal place. The distance is 95.2 centimeters. The lens is now moved closer to the fixed point, and the new distance is 93.7 centimeters. This has been shown in the next slide. So the lens has actually moved between these 2 points. Obviously, we can tell this distance by simply subtracting. But then, how about the uncertainty? Remember, the uncertainty in this is plus or minus. This uncertainty has been given as, okay, it is a meter ruler. The uncertainty in this could be plus or minus, say 0.1 centimeters. The uncertainty in this could be plus or minus 0.1 centimeters for a meter ruler. But the difference in these two values is 95.2 minus 93.7, which gives you 2 point, is it 2.95.7.2 minus 93.7. Sorry, it is 1.5. So I have to rub off that. So this is 1.5 centimeters. But how about the uncertainty? So uncertainties, although we have subtracted those values, the uncertainties cannot be subtracted. So you can't say that uncertainty in that measurement is actually zero. Instead, the uncertainty in that measurement, the uncertainty in that distance moved is actually going to be the sum of these two uncertainties. That will be plus or minus 0.1 centimeters. So you should be careful where measurements are actually or where values have been subtracted so that you do not actually subtract the uncertainties. So throughout AS and A level, we are going to meet many different measuring instruments, but many times we shall always have a choice. We shall always be faced with a task of choosing the most appropriate instrument for a given measurement. I want to give an example. A stopwatch, for example, may be suitable for measuring the time of oscillations of a pendulum. But now think of a situation where you drop a stone from a table which is 1 meter from the floor, and you have to use a stopwatch to time that event. You will notice that a stopwatch will not be convenient to time a very short distance if the object is falling from the table. If the object is to fall 1 meter, before you start the stopwatch, it will have landed on the floor. Therefore, you will need a better method of measuring such time for short distances or very fast distances, very fast movements. Light gates would be better for such an experiment. Sometimes you may have the correct instrument or an instrument that can give you a measurement, but then you have to use it creatively. Think of a situation where you have to measure the dimensions of a page of your physics textbook. Of course, to measure the length, the width, it is easier to use a ruler. You can still go ahead and measure the thickness using a ruler. You can still use a ruler. But of course, for more precise values, you would use either a vernier caliper or a micrometer screw gauge. That would be easier. But suppose you want the thickness of just one page of your physics textbook. None of those instruments is most likely going to give you a more appropriate value. Therefore, in such cases, creativity is going to be of essence. Think of a situation where you measure the thickness of all the pages of your book and maybe divide by the number of pages. Instead of using the micrometer screw gauge to measure the thickness of just one page, you would measure the thickness of all the pages and then divide by the number of pages, simply because if you were to take a measurement of just one page, you may find out that actually the uncertainty in the instrument is bigger than the measurement you have taken. But taking measurements of so many pages, you would notice that the uncertainty is smaller for a large measurement. Therefore, sometimes a correct technique of taking a measurement would also improve the results of the measurement. I hope that is understandable. So I have explained all this. In conclusion, we have seen all this. We have seen this example. Here you have an exercise to attempt. So I have said the choice of the instrument will determine on the measurement to be taken. Some measurements would require that you choose an appropriate instrument, putting in mind the precision you need. Maybe let me try one for you. Suggest appropriate instruments for the measurement of A. The discharge current of a capacitor of the order 10 power negative 6 amperes. That is a very small current. An ordinary ammeter in the laboratory may not easily measure such a current. So you may need an instrument which would measure such a small current. For example, you can use Remember a capacitor, of course we shall see this in A level, but a capacitor, we want to measure the discharge current in a capacitor. First of all, it is very small, and a capacitor charges and it discharges, charges and discharges. So we are most likely going to use either an AC voltmeter, or you could even use a calibrated CRO, that is a cathode ray oscilloscope. You can try to attempt the other questions. The time for a feather to fall in air through a distance of about 40 centimeters. Of course, a feather being light, air resistance can affect its free movement, so it may take some time. Then the length of a pendulum having a period of about 1 second, you can think of the instrument. The temperature of some water as it cools to room temperature. The temperature of a roaring Bunsen flame. Roaring Bunsen flame. I don't think you can use an ordinary thermometer to measure such a temperature, but you can use a thermocouple. So this one, I think you can use a thermocouple. A thermocouple. The weight of 20 small glass beads, I think that one you can find. The weight of a house brick, that one you can also find. Here you have trial questions. The diameter of a ball is measured using a meter rule and two set squares, as you can see. Each reading has an uncertainty of plus or minus 1 millimeter. Calculate for the diameter of the ball the actual uncertainty, its percentage uncertainty, and then suggest an alternative but more precise method by which the diameter could be measured. Okay. Next, we shall be looking at systematic and random errors. We have seen that accuracy is affected by a systematic error. Precision is affected by a random error. So what is a random error and what is a systematic error? Let's understand this very fast. So we are saying not only is the choice of instrument important so that any measurement made is with acceptable precision, but also the techniques of measurement must optimize accuracy. For example, or that is to say, not for example, your experimental technique must reduce as far as possible uncertainties in readings. These uncertainties are classified into two. We have what we call random and systematic uncertainties. So what is the difference between these two? Number one, what is a systematic uncertainty? So to begin with, let's begin with the systematic error. And remember I said the word error does not mean that there is a mistake. So a systematic error is that type of error which will make all the readings to deviate in one direction from the true value. In fact, it will make all readings to either be above or below the true value by a constant amount. Think of a simple example. Before you use a Newton meter to take a measurement, it is already reading 0.2 newtons. What does that imply? Every time you use that same instrument, it will give a reading which is 0.2 greater than the real value. Therefore, 0.2 is going to be called a systematic error. And to be specific, that systematic error, that measurement which the instrument gives before it is being used is called a zero error. So every measurement you take using the same instrument which reads 0.2 newtons before it is used, every measurement will be above by 0.2. So a systematic error is basically making readings to be above the true value or below the true value, but not both at the same time. There are basically three important examples of systematic errors that I want us to discuss. Number one is a zero error on an instrument. This one I've already mentioned it. Look at the illustration here. Let's assume before the instrument is being used, the pointer is actually below zero. It means every time I take a measurement using this instrument, the reading will be less than the actual value. So this is what we call a zero error. The instrument is giving a reading before it is being used. Therefore, before using an instrument, always check for the zero error. We check for the zero error before starting the experiment. And if we know the zero error, we can always subtract it from every measurement that we take. Number two, we have what we call wrong calibration of the scale. Have you ever tried to measure the same distances or the same lengths using three different rulers and you end up getting slightly different values? The values may vary in at least 0.1 centimeters. That is approximately 1 millimeter. Have you ever tried to connect ammeters in a series and you notice that they don't read exactly the same or give exactly the same value of current? Have you ever connected several voltmeters in parallel across the same component and they don't give the same reading? This could be as a result of these instruments being wrongly calibrated. However, we may easily know that the instrument is wrongly calibrated. Unfortunately, we may not have anything left in our reach to do to check, to remove or to correct the calibration. Although we may know that there is a problem with the calibration of a given instrument or of given instruments, for example, by connecting ammeters in series in the circuit, or connecting voltmeters in parallel, or by taking the same measurement using several rulers or a few rulers alongside each other. But then the question would be, which of these instruments is correctly calibrated? That is a very hard question to attempt. So we can only be aware that there is a problem with the calibration because the different instruments are not agreeing on the same measurement. So wrong calibration may cause a systematic error. Number three, we have what we call reaction time. Sometimes when you start the stopwatch, there is a reaction time which for a normal human being is approximately, I think, 0.2 seconds. Most likely you are going to be reluctant to start or to stop a stopwatch by about 0.2 seconds. This is what we call reaction time. Of course, reaction time affects values. Reaction time cannot be avoided because it will always be there. It is natural that uh, timing experiments manually, for example, is most likely going to introduce a delay, which is natural. There could be other systematic errors which could be due to environmental factors. For example, it could be weather condition on a particular day. If you perform an experiment on a particular day and yet that experiment is affected by weather, then it means every time you carry out that experiment on that same day where the weather affects the experiment, there will always be a systematic error. If you are, for example, trying to measure the specific capacity of seawater and some energy is lost to the surrounding, then you also expect a systematic error. But the most common systematic errors we shall always concentrate on are actually zero error and maybe wrong calibration. Those are the most common ones. These others are just for personal consumption, but still they can affect experimental observations. So a systematic error, in summary, will always make values to be either above or below the true value, but not at the same time. So normally measurement is given plus the error or a measurement is given minus the error, not both at the same time, because the systematic error makes all readings to deviate in one direction. So here I have a distribution graphs. We have in red, we have distribution of x when there is a systematic error, and in blue we have distribution of x with no systematic error. So notice that the systematic error does not affect the average. We call this a bias. So a systematic error will not affect the average. Still values, the average value, as you could see here, in red, this has an error. In blue, this is with no error. So you notice that there is a difference between the average of the true value and the average of there's a difference between the average when there is no systematic error with a systematic error and the average with no systematic error. Actually, the systematic error affects the average. It affects the average. The average value of frequencies with no or values of x with a systematic error is not the same as that with no systematic error. So there is this gap here between the average values. So systematic error affects the average, and I said we call this a bias. The measurements are always above, or the average is always above, or it is always below the true value, but not both at the same time. Okay. On the other hand, we have also talked about the random error. Random, the word random, it is unpredictable and will always be present. Random errors will make readings to scatter about the true value. That's why we mentioned them when we were dealing with the precision. Because they make values to scatter around the true value, they are responsible for the range between the values. Take for instance, if you take readings from a scale, every time you take a reading, you take readings from different angles. What is the implication? Every time you vary the angle from which you take a reading, then it means you are most likely going to give or to estimate readings differently. So, and you cannot take readings from the instrument at the same angle every time. So random errors are actually unpredictable and they will always be present. Of course, systematic errors may not be present every time because they depend on the instrument, and therefore if it is a zero error, you can remove it and use the instrument perfectly well. There is no systematic error. But for random errors, they are out of the reach of the experimenter. You cannot always take a measurement from the same position. You cannot always take a reading from the scale from the same angle. Therefore, random errors will cause readings to scatter about the true value. Because they scatter about the true value, the readings will either be above or below the true value. That means they do not affect the average. The average is not affected. And because the average is not affected, the accuracy is not affected. In fact, when there are random errors, you may find that the average value of all these measurements is actually the true value. Unlike a systematic error which affects the average, the random error does not affect the average because it makes values to be either above or below the true value. And we have already seen that random errors may be reduced by repeating the experiment and obtaining the average, or plotting the graph and obtaining the line of best fit. Obtaining the average, because the average value of all the measurements is most likely going to be the true value. The accuracy is not affected by random errors. Precision, random errors do not affect accuracy, they only affect precision. Systematic errors will actually not affect precision, but will affect accuracy. So I want you to note that very well. A random error will affect precision but not accuracy. Yet a systematic error will affect accuracy but not precision. All values may be above the true value but when they are close to each other. All values may be above the true value, that is when there is a systematic error, but when they are all close to each other. So when we look at a graph, when we look at the distribution graph, but before we look at the distribution graph, we can talk about the most common examples of random errors. Number one, we have what we call wrong interpolation between scale divisions. Wrong interpolation between scale divisions. What do I mean? Let's assume you are taking a reading from the ruler and this is the measurement you are taking. Sometimes you may approximate this to half of a division, sometimes you may approximate to be close to this mark here. So taking a reading between two divisions or between scale divisions is what we call interpolation. So one major example of a random error is actually wrong interpolation between scale divisions. Wrong interpolation. Wrong interpolation between scale divisions. I've explained what I mean by interpolation. You are taking a reading between scale divisions. Sometimes you approximate to be half a division. Sometimes you approximate to the next mark or the next scale reading. That is interpolation. Number two, which is also very common, is taking readings from different angles. Taking readings from different angles. Taking readings from different angles is also going to introduce a random error. Every time you look at a scale, you may not look at the scale at the same angle as you did in the previous measurement. This also introduces what we call a systematic error. Number three, which is also important, if we are timing oscillations, many times we don't count oscillations from a reference mark. We normally don't count oscillations from a reference mark. So when we are timing oscillations, sometimes even the amplitude gradually reduces and we still count them as full oscillations. In the practicals, we improve this by counting oscillations from the center or from the middle, where we place normally the mark. So timing oscillations without using a reference mark is also introducing a random error. Sometimes we say taking readings from different angles introduces what we call a parallax error, because every time you vary the angle, from which you take a measurement, then you are most likely either overestimating or underestimating a measurement. So that one is most likely introducing a random error. Okay, so normally the measurements here, unlike for systematic, these are given as plus or minus. They can be the first measurement can be above and the second measurement can be below. So they are normally given as plus or minus. The measurement for a random error is given as plus or minus. And therefore, because it is plus or minus, if in blue we have a distribution of x when there is no random error, and in green we have a distribution of x with a random error. The distribution of x with the random error is just making values to scatter around the true value, but the average, you notice that the peaks are coincident here. So the average is not affected. So a random error does not affect accuracy because it does not affect the average. It only affects precision. That's why you see the range has actually increased, but the average value is actually the same. A random error does not affect accuracy, it simply affects precision. Okay, so having seen that, we can come up with a conclusion. To reduce the effect of random errors, we normally take multiple readings. When a series of readings are taken, then the arithmetic mean, which is the average, is the most probable answer. And the greatest deviation from the mean is what we call the absolute error. The deviation from the average is what we call absolute error. And here are general examples that I think you can also attempt. The current in a resistor is to be measured with an ammeter suggests one possible source of a systematic error. What will cause a systematic error? We have said there are two major causes, the zero error. If there is a reading in the ammeter before taking a measurement, then there is a zero error. We expect also because it is analog, it is most likely going to be wrongly calibrated. Those two values, those two examples of errors are actually systematic. Random error. A random error is most likely due to taking readings from different angles, wrong interpolation. It could be parallax error caused by taking readings from different angles. It could be wrong interpolation between scale divisions. How do we reduce a random error? We said normally, if you are taking a reading from a scale, you can place a mirror behind the scale and then you view normally. If this is the scale, I put a mirror here. So if this is a scale, if this is an analog scale and I have placed a mirror somewhere here, then an image of the pointer or an image of a scale division will appear in the mirror. So if this object is perfectly in line with the image, then there is no parallax. Therefore, the measurement would be actually acceptable. Self-check. It's now your turn to attempt this self-check. The length of a pencil is measured with 30 centimeters with a 30 centimeter ruler. Suggest one possible source of a systematic error, a random error. In each case, suggest how the error may be reduced. The diameter of a wire is to be measured to a precision of 0.01 millimeters. What is the suitable instrument? Suggest a source of systematic error. Explain why it is a good practice to average a set of diameter readings taken spirally along the length of the wire. I think you should be able to attempt that self-check. In case you find a challenge, you can go back and review all the slides. And then as you attempt the self-check, you develop concepts. You should now be able to distinguish between accuracy and precision. Accuracy is referring to how close the measured values are to the true value. How close the average value of the measurements is to the true value or to the expected value. Precision, how close the measured values are to each other. A systematic error are those errors, or a systematic error is that error which makes all measurements to either be above or below the true value by a constant amount. A systematic error affects the average value because the average will always be either above or below the true value. A random error refers to that error which makes values to scatter around the true value. A random error will make values to scatter around the true value. Therefore, it does not affect the average, it only affects precision. So in conclusion, a systematic error can be eliminated but cannot be reduced. It affects accuracy. A random error cannot be eliminated, it cannot be predicted after all, but it can be reduced, and random errors are always present. These only affect precision but not accuracy. I think we have come to the end of this presentation. Something, and I thank you for watching this video. Have a good night. Bye bye.